Hello and welcome to this video lesson on patterns and relations where we will focus on understanding equality. Let's begin by looking at our learning and language goals. Our learning goal is, I can demonstrate and explain the meaning of the preservation of equality concretely and pictorially. And our language goal is, I can talk about equality using words like equals, equality, equivalent, and the commutative property. Take a look at this photo. What would happen if the boy decided to pick up his backpack? When we talk about equality in math, we can use balance scales to represent equality pictorially. So when I say pictorially, I mean using pictures. We also call this kind of scale that you see on the screen here a pan balance. So we may call it balance scales or a pan balance. We imagine an equal sign in the middle of the scales between the two pans to show that whatever value is in the left pan must equal what is in the right pan. We can put an expression on the left side of the balance scale. In the left pan, in this case, I have the expression 2 plus 2. To keep the scales balanced, what number must be on the right side of this balance scale? Since both sides of the scale must have the same value in order to stay balanced, the number on the right side of the scale must be 4. We can put expressions on both the left and right pans of a balance scale like this. Is this scale still balanced? Yes, it is still balanced because both sides represent the value 5. Here are some more examples. Each of the scales that you see on the screen here are balanced. For each of the balance scales, the expression in one pan is equivalent to the expression in the other pan. We use the equal sign to show that the two expressions are equivalent. For the first example, 36 divided by 6 equals 6, and 15 minus 9 equals 6. So 36 divided by 6 equals 15 minus 9. For the next example, 12 plus 5 equals 17, and 5 plus 12 equals 17. So 12 plus 5 equals 5 plus 12. And finally, 3 times 7 equals 21, and 7 times 3 equals 21. So 3 times 7 equals 7 times 3. This is a good time to stop and go over some key vocabulary. You may have noticed that I said we use the equal sign to show the two expressions are equivalent. It's important to know that in math, equivalent is not quite the same as equal. Equal means the same in all aspects, whereas equivalent means similar but not identical. For example, 2 is said to be equal to 2, but equivalent to 1 plus 1. And the word equality refers to the relationship between two quantities or expressions that have the same value. For example, 3 times 7 and 20 plus 1. The two expressions both represent the quantity 21, therefore they are equivalent, and their relationship to each other shows equality. Let's check to see if we can apply our new understanding. If 3 times 7 equals 21, are they equivalent or equal? They're equivalent. That's because while the expression 3 times 7 does represent 21, they are not exactly the same in all aspects. How about 6 times 2 and 4 times 3? Are they equivalent or equal? They're also equivalent. Again, both expressions represent the quantity 12, but they're not exactly the same in all aspects. Okay, and last but not least, 2 times 4 equals 2 times 4. These expressions are equal. We know this because they are exactly the same in all aspects. Now, for grade 6, it's fine for you to think of the words equivalent and equal as synonyms, but I know it can be confusing to see words that look related, and these clearly are, and not know if there's a difference between them. So I wanted to explain it to you. Give this one a try on your own. Is this scale balanced? Did you say yes? If you did, give yourself a big old pat on the back. Both sides represent 153, so the scale is balanced. There's actually another way we can tell the scale is balanced even if we don't know what the expression represents, and that's called the commutative property. We can use the commutative property to show that the scale is balanced. Now, the commutative property is a math rule that says that the order in which we add or multiply numbers does not change the sum or the product. And this is a property that I've talked about lots, so I'm hoping that this is not completely new for most of you. But before we move on, let's quickly review some math vocabulary here. Sum is the word that means the result of addition. So if I asked you to give me the sum of 3 and 2, you would go 3 plus 2 equals 5, and the sum would be 5. All right, back to the commutative property now that we all remember what sum means. When we add two numbers, their order does not affect the sum. The scales always balance. This is called the commutative property of addition. We can use variables to show this property for any pair of numbers we add. So we can see here on the picture, the example says 1 plus 4 equals 4 plus 1. And we can see that we switched those numbers around and it doesn't change the sum. The sum is still 5. 1 plus 4 is 5. 4 plus 1 is 5. That's the commutative property. Now that we know how to use variables, we can remember this equation, a plus b equals b plus a, to help us remember the commutative property. So any two numbers added together, you can switch their order and it doesn't change the sum. Multiplication is also commutative. When we multiply two numbers, their order does not affect the product. Now, let's recall that product is a word that means the result of multiplication. So if I asked you to give me the product of 3 and 2, you would multiply 3 times 2, and the product would be 6. The commutative property of multiplication states that the order in which we multiply numbers does not change the product. And again, we can use variables to show this property for any pair of numbers we multiply. So a times b equals b times a. And you see in the picture, we have 3 times 4 equals 4 times 3. If we simplify those expressions and find the product is 12, whether we do the 3 first, 3 times 4, or the 4 first, 4 times 3. That's the commutative property. It applies to both addition and multiplication. We can write expressions using the commutative property. Let's give it a try. 15 plus 6 is the same as 36 plus 15. The commutative property of addition tells us that changing the order of the addends, that's the two numbers being added together, doesn't change the sum. Let's try it with multiplication. 8 times 6 is the same as 6 times 8. In this case, the commutative property of multiplication tells us that changing the order of the factors, that's the two numbers being multiplied together, doesn't change the product. Suppose you're using real balance scales. Which of the scales below would balance? Did you say A and B? If so, you got it right. Give yourself a big old pat on the back. The expressions in both pans on scale A are equivalent to 8, so it's balanced. And we can use the commutative property to tell us that scale B is balanced, or we could work out the product in both pans is 72, and so they're equal. And the pans on side C are not equivalent. 19 minus 9 equals 10, whereas 9 plus 19 equals 28. 10 and 28 are very different numbers. Let's recap what we covered in today's lesson. We can use balance scales to represent the relationship of equality. If the value in both pans is the same, we say they are equivalent. When two quantities or expressions are exactly the same in all aspects, we say they are equal. The commutative property of addition tells us that the order in which we add numbers does not change the sum. And we can use variables to show this property. A plus B equals B plus A. And the commutative property of multiplication tells us that the order in which we multiply numbers does not change the product. Again, we can use variables to show this property. A times B equals B times A. And with that, I think we are well on our way to a solid understanding of equality.